Yeah. So, hello everyone, and happy to have you here in our today's colloquium. So today's speaker is Matt Middleton, and a few words about Matt. He started his venture in astrophysics in the mid-2000s at the University of Durham, where he gained his PhD working with Chris Don in the intriguing topic of the properties of AGN in the context of X-ray binaries. So he found, for his PhD, he found evidence that spectral state transitions in vary with mass accretion rate, much in the same way of FXRBs and AGNs. And he also discovered an hour-long QPO signal for the first time in AGN power spectra. Then he continued working as a research associate at the University of Durham before becoming a Marie Curie Fellow, working in Anton Pannekow Institute in Amsterdam. And gradually he started working more and more into stellar mass, black holes and microquasars and ULXs. So in 2016, he went back to the UK and the University of Cambridge, working with Andy Fambian. And then he became an Ernest Rutherford Fellow, first in the University of Cambridge and then in Southampton. And around 2018, if I'm not mistaken, he became an associate professor at the University of Southampton, and he has been conducting research with some amazing young researchers and young PhD students. And much of his research work involves the study of ULXs, and in particular focused on the outflows during super-Eddington accretion regime from the accretion disk. And he started conceptualizing a model about the spectral timing variability of ULXs in the supercritical regime. And I think this will be some, at least, of the focus of today's talk. And I think I should say that I have been always working on similar stuff with Matt the last few years, and I always find his work interesting. And I hope you all enjoy today's colloquium. And hopefully within the next years, on less busy times, we will have the pleasure to have you here or in Athens in person, Matt, and have interesting discussions back again. So thank you, everyone. And Matt, the floor is yours.
Well, thank you for a lovely introduction, Jonas. And also, you're I think you're the second person who knows the name of my thesis after myself. So that's amazing. So thank you so much for inviting me. So I probably won't talk about much timing stuff, just to disappoint you. But this is a sort of a view into some of the stuff that I'm doing, some of the stuff that I find interesting. It certainly shouldn't be viewed as everything about this topic. It's very, very broad. Just would tell you there's a lot of stuff to do, and it's fairly complex and fairly exciting. But I'm going to dive straight in because the central bit of what I do is looking at Eddington accretion. And I don't know the range of the people who are on this talk, so I just wanted to put some nice basic stuff in. So what we can imagine is that we've got a gravitational potential, material falls into it at some rate m dot, and we can extract some luminosity out of that. From the virial theorem, we know that's half the gravitational potential energy. So we get some luminosity out, and the limiting luminosity we get out is the Eddington luminosity. So this is the point where the push due to radiation balances the inward pull due to gravity. And we can write a nice simple equation where we have m dot Eddington is equal to the Eddington luminosity divided by eta c squared. And eta here is our radiative efficiency. It's how easily we can convert mass into energy. Now, if our actual accretion rate in our system is less than the Eddington mass accretion rate, we say it is sub-Eddington. If it is greater than or equal to m dot Eddington, we say it is super-Eddington. Some people also call it supercritical. The terms are essentially interchangeable. Now, what the picture I've got there is actually talking about spherical accretion. And in reality, most material, when it's falling into a gravitational potential well, has angular momentum, which means that it has to form an accretion disk. And this is really, really important because not only is the radiative efficiency different, it's much higher through a disk than it is through a spherical infall, we can also have radiation escaping perpendicular to the direction of infall, and that really does make a substantial difference. So that's kind of the basic bit about Eddington and m.Eddington. It's also, it should happen, right? We should be able to feed objects at greater than the Eddington mass accretion rate. And there are a few examples that I just want to give you. Now, these are all related to accretion onto stellar mass compact objects, by which I mean black holes and neutron stars. I'm not going to talk about AGN, even though they're a fascinating topic and there's wonderful stuff being done on them, especially around Eddington accretion. I'm just going to focus on the binary systems. So here is a star. It has evolved on the nuclear timescale to fill its Roche lobe. Material crosses through the inner Lagrange point and it forms an accretion disk due to viscous dissipation carrying angular momentum both inwards and outwards. And the approximate rate of infall is the mass of the secondary star divided by the nuclear timescale, which makes perfect sense because we're expanding that star inside its Roche lobe. And there's lots of great phenomenology on here. This isn't to talk about X-ray binaries necessarily. You know, there's lots of cool stuff in there I won't talk about. Another way of generating very rapid mass transfer onto our compact object is doing so on a thermal timescale. So for instance, this can happen during the Hertzsprung gap, where our star very rapidly fills its Roche lobe. And if we have a very large companion star, so in terms of mass, so it's much heavier or is at least approximately as heavy as the compact object, then mass loss tends to shrink the Roche lobe. As it does so, the star wants to try and regain some sort of equilibrium, and it can do this as long as the envelope is radiative, because you can readjust a radiative envelope. You can't readjust a convective envelope. And the timescale, so the mass rate that's pushed through onto the compact object is now the mass of the companion star or the donor star divided by the thermal timescale. The thermal timescale is much shorter than the nuclear timescale, so this can lead to very high mass transfer rates in excess of m.Eddington. Another way is that in very massive stars, for instance, red supergiants, you can be losing up to 10 to the minus 4 solar masses a year. Now, don't worry about those units, but that's very, very high in terms of m.Eddington. And if you can gravitationally focus that down onto the compact object, again, you can generate very large mass transfer rates compared to just spherical infall, which is described by the equations of Bonney-Littleton-Hoyle. So those are three ways that we can generate mass accretion rates or mass transfer rates which are greater than m.Eddington. So theoretically, this should be absolutely possible. And we see strong evidence that these mass transfer rates down to the compact object are occurring in the local universe. On the left-hand side is one of the most fascinating objects in the galaxy. It's called SS433. Hopefully many of you have heard of it. If you've worked on it, you know it's a real pain to try and work on. It's also described as the Manatee Nebula, because that image on the top, which shows you the radio emission, it kind of looks a bit like a manatee. And you can see there are powerful jets being fired out from somewhere near the middle, and these are expanding to fill this cocoon. The mass transfer rate through from the donor star to the compact object or near to the compact object is again 10 to the minus 4 solar masses per year. What that really means is that'd be around 3,000 Eddington for a neutron star or 300 Eddington for a stellar mass black hole. So truly super Eddington. On the right-hand side are jet ejections from GRS 1915 plus 105, another very famous X-ray binary in our galaxy, another complete pain to work on. I've worked on both of these things. And these are, and GRS 1915 is accreting close to its Eddington limit. It has been for many, many years, although recently it's done some strange things. And it ejects these powerful blobs of material away from close to the black hole. So we definitely see super-Eddington accretion in X-ray binaries. We also know of super-Eddington accretion in other ways. So we know about tidal disruption events. This is a very important area, growing area in transient astronomy. And also Eddington and super-Eddington accretion onto supermassive black holes, especially the very bright quasars. So super-Eddington accretion should happen. I haven't talked about how you feed supermassive black holes at super-Eddington rates, and I won't. It definitely happens in the local universe, and we really want to understand it. There are many reasons why you might want to understand it. Super-Eddington accretion leads to a lot of feedback of energy into the local environment, so it's no doubt important for things like star formation. But also, it's really important if we want to understand cosmological evolution. So this is quite an old picture now, but I do like to show it because what it's demonstrating is that supermassive black holes, or some of the biggest ones, were already grown at very high redshift. And in order to do that, you basically had to feed your supermassive black holes at super-Eddington rates. And whether or not you started from a population 3 remnant or you started from an intermediate mass black hole, this remains true. So in order for us to understand super-Eddington, understand this growth and what that meant for the universe, we have to have a practical understanding of super-Eddington accretion. So that is the motivation for doing so. So what does theory tell us about what happens when we put through material towards our compact object? For context, I'm going to provide the picture for sub-Eddington accretion rates and then super-Eddington. So at sub-Eddington rates, we have a geometrically thin accretion disk. So it's presumed to have a scale height, so h upon r, very, very small. That's because it can cool very efficiently, so it remains very, very thin. And that emits as a sum of black bodies locally, because it's optically thick, so it thermalizes very efficiently. So that picture on the right-hand side just shows you just a combination of all of these black bodies together. I'm sure you're all familiar with those equations. In addition to black body emission, there's also a corona of hot electrons. That's probably a mixture of thermal and non-thermal populations. And this upscatters photons from the disk and produces our Compton tail. So that's what it kind of looks like at sub-Eddington rates. At super-Eddington rates, things change quite a lot. So our material is coming through the disk, and the ability to convert mass to energy actually depends upon radius, depends upon the depth inside our gravitational potential well. And so you can actually reach the Eddington limit quite a long way from our compact object. This first happens around what we call the spherization radius. And don't worry about taking these equations into your mind, but it's approximately the inner edge of the accretion disk, so what we call the ISCO, multiplied by the Eddington scaled accretion rate. And you can understand that in terms of the fact that the radiative efficiency scales as 1 over the radius in the disk. So there's simple ways to understand it. So what this does is that at the point around the spherization radius, we reach Eddington, the radiation pressure is enormous, so that pushes up the scale height of our disk. So it goes from being thin to suddenly very thick. And if we turn up the accretion rate even more, that spherization radius starts further out in our accretion flow. Okay? Now that's fine, but if we're coming in with super-Eddington accretion rates and then we reach that point first in the disk where we have an Eddington luminosity coming out, if we move further in with the same amount of material, we're suddenly going to be further into our gravitational potential well, we're going to have extracted even more energy, and we're going to be super-Eddington. We don't want that, because that really will blow our accretion disk apart. So to avoid that, we need to lose material. And it does this through a wind, so a mass-loaded wind. And that carries quite an enormous amount of kinetic luminosity. And that's going to be really important for when you try and interact with the local environment. So the accretion luminosity scales as the Eddington luminosity multiplied by 1, which is your thin disk until you reach the spherization radius, plus this funny value of the natural log m dot naught. And m dot naught, remember, is our Eddington scaled accretion rate. So that's fine. So you can immediately see that if m dot naught is of order 100, 1,000, you can get a few times Eddington out without doing anything else. Like, you've not broken physics, you've not somehow avoided gravity and radiation. It's still completely fine. This is because radiation is emerging perpendicular to the direction of gravity. There's another important effect though, because we've increased the size of our accretion disk, the vertical size, and we have these mass-loaded optically thick winds that can trap radiation. So the radiation can just scatter around inside this wind cone. And so now our opening angle isn't 4 pi, as we tend to assume, it's smaller than that. We have an opening angle which goes as omega over 4 pi, and that's related to the opening angle in the apex of our cone. We describe this with a little b, so that when we work out our observed luminosity, it should go as something like 1 plus, and now that little natural log m dot naught has got a b under it. So b is always less than or equal to 1. And that can take us from being a few times Eddington to tens, maybe even more times Eddington. So that collimation, what we call geometrical beaming, not to be confused with relativistic beaming, may be really important. Not only, and this is just really for the experts who probably more for judge us, but actually we don't really know much about this beaming factor. Theoretically, we haven't even explored its dependence with radius, but as we move further out in our flow, that beaming function does change. So how do simulations, which carry most of our understanding of physics and the coupled behavior of magnetic fields and fluid dynamics, so MHD, how does that look compared to analytic theory? Because we'd like it to look kind of similar to know we're on basically the right path. And it seems as if it's telling us that we've kind of understood a lot of it correctly. So these are simulations carried out by a collaborator of mine, Yanfei Zhang, going back to 2014 now. It's really seminal work. A material comes in, there's an MHD dynamo, so it drives real viscosity, and then you reach the Eddington limit, everything puffs up, and we lose material. So you know the scales on the vertical axis, that's a pseudo density, so that really will mean nothing. And the color bar on the top is the velocity of material in units of the speed of light. So you can see that in the middle, in that cone, you've got very low densities, and material is moving very, very rapidly. And as you go further out, we've got winds that are being driven, and they're somewhat, they're denser for sure, and they're moving slower. Now, the MHD simulations of the super-Eddington accretion, they also capture effects that we could never hope to gain analytically, such as things like magnetic buoyancy. And that's where you lower the density of plasma around magnetic fields, and that allows them to rise up through the disk, through the flow. They also confirm that geometrical collimation is present, and it's of order a few. So that's fine if we have a black hole, but what happens if we have a neutron star? So again, I'm sorry, I don't know how many people there work on neutron stars. They're really fascinating and quite difficult. Well, then what happens is that we could have not only surface effects, but neutron stars have strong magnetic fields. And magnetic fields can truncate the accretion flow. They truncate around what we call the magnetospheric radius, which is close to the Alfvén radius. So then what happens is the material is going to come through the thick disk, and then it's going to fall onto the neutron star on basically a free fall or a dynamical timescale. Now, the actual nature of the accretion flow within the magnetospheric radius is kind of complicated. I'm not going to go into it in any great detail. It depends very much on the field strength. It depends on the field geometry, the neutron star spin. But one of the key results of this is that if we have a misaligned spin axis with magnetic axis, then just like with radio pulsars, we should be able to detect pulsations, only this time in the X-rays. The luminosity, by the way, now no longer looks like that very simple equation I showed you before. This equation probably you don't need to know. We also have simulations now of super-Eddington accretion onto neutron stars, and they seem to carry a lot of the similar information as we see on black holes. You still see powerful winds being driven. These are some really important simulations done by Takahashi et al. And I show another one later for a different field strength. So what does it mean when we're trying to observe these systems, these theoretical super-Eddington systems? First of all, there will absolutely be an inclination dependence to them. So if we're looking face on and we're looking down that cone of the wind, we're going to see collimated emission, and that is going to be coming from the hottest regions of our accretion flow, so the X-ray bright regions. So we should exceed extremely X-ray bright emission. And as we move more and more edge on, because there must be many edge on systems, our X-ray emission starts to decrease and our lower frequency emission starts to increase until eventually we're edge on and we see no X-rays at all, or very little X-rays, but a lot of emission emerging at lower energies. And the emission from the outside, which is quasi-spherical, should be around about the Eddington luminosity. In terms of X-ray spectra then, what you can imagine are these two situations, so a bracketed face-on and edge-on. If we're face-on, you'd see some very, very low amount of emission due to the edge of the photosphere, which is seen very bright edge-on, that's in purple. you would see thermal emission coming from the accretion disk. And then as you get deep into the cone, you see very, very bright, hard X-ray emission. So that's the thing on the left. As we move edge on, we're now dominated by low energy emission coming from edge on and the photosphere of the wind. We're going to see less of the emission coming from the disk, and basically little to no emission coming out in the hard X-rays. If we have a neutron star, the picture is fairly similar. The only thing is that when we're face on, we also have emission from close to the neutron star. So where that material is falling down into what we call an accretion column, and that's where the pulsations come from. That's given by that cyan line. But essentially, they should be fairly similar for this type of geometry. Not only is there an inclination dependence to the continuum emission, we should also expect to see an inclination dependence due to atomic features. So when we're face on to our systems, we're looking mostly at low density, fairly fast moving outflows. So they shouldn't leave very strong imprints. And if they do, they should be heavily blue shifted. As we go to higher inclinations, we're looking through more material. So the optical depth will be greater in the line, and they're slower. So they won't be as blue shifted. So we definitely expect there to be a change in both the continuum and also any atomic features that we see. And these are atomic features mostly in absorption. I won't really talk much about emission lines, maybe a little bit. And this was the simulation I was alluding to on the right-hand side, just to demonstrate that you see a similar picture in terms of inclination dependence when you start turning up the magnetic field strength of the neutron star. This is still fairly weak by neutron star standards. This is only 10 to the 10 Gauss. We know of neutron stars which go all the way up to magnetar field strength of 10 to the 15 Gauss. But I won't talk much about those very strong magnetic fields for a reason that I'll get onto in a second. So if we put those atomic features together with our continuum, then this is the picture that we sort of end up with. That face on, we have systems which should be very X-ray bright. They should have a lot of emission coming out at hard X-rays, so we call them spectrally hard, and they should have fairly weak atomic features. As we move more edge on, that hard X-rays drop away, actually makes it much easier for us to start detecting atomic features, you know, certainly in the soft X-rays and maybe even slightly harder X-rays. Okay, so that's kind of the theoretical groundwork that I wanted to go through. Now I'm going to talk much more about the observation. So if you've taken anything from that theoretical bit, fantastic. I hope that's made some sense, maybe answered some questions for you. For the observers, this is probably more your wheelhouse. So I'm going to talk about ultraluminous X-ray sources. Jonas already said that this is something that I've spent a lot of time working on. They've been known for a very long time, and they were first discovered in the 1970s. They're defined as having super-Eddington luminosities for stellar mass black holes. I don't know why I said all neutron stars, because that's not actually necessarily correct. They're empirically defined as having luminosities in excess of 10 to the 39 ergs per second. This is something that annoys the hell out of me, because that's just, it's a number that doesn't really relate to the physics. And as I've already described, if we have inclination dependent emission, then this isn't telling us an awful lot. But these are the ULXs. You can see some in the left-hand side plot where I've got the cartwheel galaxy. This is where a small galaxy smacked through the middle of the other one and triggered a load of star formation. And in that ring of star formation, there are a load of ULXs. That's already telling you something really important about the nature of ULXs. And some of them are surrounded by very large bubbles of hot gas. We call them bubble nebulae. I'll talk about them a little bit. And we believe these to be the very best places to study super-Eddington accretion and test some of those theoretical ideas. The X-ray spectrum kind of looks like this. It's very thermal, right? We don't see a lot of flat power laws. They tend to be 2-component, maybe 3-component. Easily in this image I show you on the left, you can see that that's going to be a 2-component spectrum. Important temperature for me to point out, because it comes back later in the talk, is this T-soft. So that temperature of the soft temperature, if we assume that picture that I've described before, we think it relates to radiation coming out from the spherization radius. So you remember that was this radius in the disk where we first reached the Eddington limit. And it's given by some formula, which the important thing to take from the formula is that it's related to the accretion rate, probably unsurprisingly, and the mass of the compact object. Okay, again, I'm going to use that later. And here you can see a whole bunch of ULX spectra. You can see they all look basically thermal. They all have, some of them have a couple of components, quite obviously. Some of them appear to have one, and they all have this spectral break somewhere between 2 and 10 kiloelectron volts. Fine, so we see a nice spectrum of spectra. And individual ULXs change. They don't always look the same. So their soft emission will change, the hard emission will change. You tend to see that ULXs are more variable on long timescales at hard X-ray energies rather than soft X-ray energies. And ULXs tend to be brighter when they're spectrally harder. Again, that's another important piece of evidence. And that makes perfect sense if these systems do have these wind cones, and when we're looking face down, they should be very, very bright at hard X-rays. Back in 2014, I was looking through some spectra and I noticed some residuals to these nice thermal models. And these residuals had been seen before. They'd been interpreted as due to local star formation, but the luminosity in these features was way too high for it to be star formation. So I decided, let's explore whether what we're seeing at soft X-rays, and hopefully you can see on the left-hand side, it's difficult when you haven't got a pointer. You can see these residuals to the spectral fit. And I thought, well, okay, maybe what we're seeing is the first evidence for absorption lines in these winds, because as I already explained, you should expect to see these. I did some simple modeling and it turned out the velocity was around 0.2 C. Okay, fine. Very, very fast, much faster than other winds you might see in X-ray binaries. Great, okay, that's fine. You also see these residuals basically the same energy in loads of ULXs, which is really interesting. And not just in one instrument, because if it was in one instrument, your first reaction would be, Matt, you've done it wrong. You haven't accounted for some metal line that's in the instrument. But no, you see these residuals in Swift, in Chandra, in XMM. So these are real features, and they seem to be ubiquitous in ULXs. And then in 2016, when I was in Cambridge, Ciro Pinto analyzed the RGS, so very high energy resolution instruments on board XMM Newton, and we were able to get confirmation that we're seeing broad absorption lines, blue shifted and rest frame emission lines. And because of the quality of the data, you can actually start trying to describe that spectrum with real models, not the noddy one that I made. And you get velocities of 0.2 C. So yeah, it looks like I was right with my easy model. And you get ionization parameters. And it basically confirmed that winds were happening. And this is one of the key predictions of super-Eddington accretion. So this was a huge result. And it's created a bit of a cottage industry. So people have gone off and they found more of these lines in various ULXs, which you can see here, which I won't go into a lot of detail about. And what's interesting is that the velocities are kind of similar. They're all tens of % of the speed of light, and there seems to be a bit of a variety in the ionization parameter, this log xi term. What it permits us to do, which I think is really important, is estimate the kinetic power from these winds. And you can do this with a fairly simple formula. Many of you, I'm sure, have seen it before. And just breaking down the important elements of this, we have the covering factor of the wind. This is very hard to estimate because you can either assume that your wind is completely homogeneous, or you can assume that it's clumpy. Different phases of the wind, so you could see from that simulation, some of the wind is fast, some of it is slow, some of it is low density, some of it is high density. We're only ever going to really observe the one which is the densest, because that's going to give us the strongest features. So you always have to remember that we're not necessarily probing the full system. So the filling factor no doubt will be phase dependent. We have the velocity. So remember, when you measure velocities from blue shifts and red shifts, you're only ever measuring a lower limit on the true velocity because you're looking at the projected line of sight velocity. So really it could be faster. And again, that's phase dependent, fast wind, slow wind. And the ionization state, again, obviously phase dependent because different parts of the wind see different irradiating luminosities. They have different masses. So, different number densities. So it's difficult, right? So these are only approximations, but if you're willing to believe those approximations, you end up with values in the range 10 to the 39 to 10 to the 40 ergs per second. So very much super-Eddington kinetic luminosities. You can compare those luminosities to those in nebulae. So you can look at those bubble nebulae that I alluded to earlier. Here are two pictures of some. You've got the obvious one on the left-hand side, which is Homburg 2X1, which is a fairly famous ULX, and the one on the right, which is MQ1. MQ1 actually doesn't have a ULX, but it has got this big bubble nebulae. So probably we're seeing a ULX but edge on. And you can estimate the kinetic luminosity in order to inflate this thing just through shock physics. And it seems to match very closely what we get from the wind. So perhaps, or probably, I believe absolutely, that these winds are inflating these bubble nebulae around ULXs. One of the interesting things that I've been working on very recently are what we call thermal winds. So you'll remember, I hope, if everybody's still awake, that the photosphere, when we're edge on in ULXs, should emit around about Eddington, and it should be low frequency, so it should be lower energy. But those photons should irradiate the outer disk. So this thin disk, which is coming through, that hasn't yet met the spherization radius. When that happens, what's going to happen to that material? Thermal winds have been studied in AGN and in X-ray binaries by people like Knox Long, Daniel Proger, Christian Knieg, Nick Higginbottom, and they've been shown to be so important because they can actually drive all of the material away from the accretion flow. So thermal winds are super important, and we've, for the first time, explored these in ULXs. What happens then is your photons come in and they can basically energize the atmosphere, and if that gas becomes energetic enough, it can just leave the disk. So it can carry loads of material away. And the region that occurs is called the inverse Compton radius. So what I did was I took the standard formulae for supercritical super-Eddington accretion. We can determine the position of the photosphere for a black hole or a neutron star. This is an equation that I think first appeared in Judges' paper and then appeared shortly after in mine. And we can work out the temperature of the photosphere. And then so that tells us what our SED is that's irradiating the outer disk. And then we can just work out, is our material out in the outer regions unstable or stable to this irradiation? And these are what we call S-curves. Again, don't worry too much about the details, but if you have a negative gradient, that's a region of instability. And so what I'm plotting here are a load of different temperature SEDs. They're all black bodies. And you can see that it starts to become unstable around 10 to the 7 Kelvin. And then what happens is that when we start heating the gas, it jumps up very quickly to the inverse Compton temperature. And you stick that into 3/2 kT, compare it to the local binding energy, and then work out, are you losing material? And it turns out that we should be losing a lot of material from these ULXs. In fact, we lose all of the mass if we have photospheres which are hotter than around 10 to the 6 Kelvin. So this is a really intriguing problem that I'm still sort of working out and cogitating on. But what it might do, in that left-hand plot, you can see the velocity of the material in units of 10 to the -3 C. So this is way slower than those winds that we've seen in ULXs before. So maybe this is providing some of those rest frame emission lines that Ciro Pinto discovered in 2016. And the game changed in ULXs around 2014 because Matteo Becchetti and the New Star team demonstrated that we could have neutron star ULXs, which, by the way, were already known about. We already knew about systems which were above 10 to the 39 ergs per second. But he demonstrated that there's an object in M82, which was 100 times Eddington for a neutron star. We see pulsations in it around about 1 second, so we know it's got a surface. It's definitely going to be a neutron star, can't be a white dwarf. And this really changed the field because now we had to, originally the argument was, what is the mass of the black hole? Now the argument is, we've got neutron stars. What are the nature of these neutron stars? How many are there? What are they like? We know of around about 10 neutron star ULXs now in a population of hundreds of ULXs, but we think there should be a lot of neutron stars out there. They're very difficult to study. These pulsations aren't always very strong, and you need good quality data. And also they come and go, which just makes life a million times harder. For the people, you should never put a table in a talk, by the way, for those of you who are young. The reason I put this in here is to really advertise the fact that there's going to be a review coming out very soon that contains all the information you want to know about these systems, including the thing I've highlighted is the spin-up rate, so how quickly angular momentum is being dumped onto the neutron star. Some of these numbers are extreme, but you can also see the pulse period is, of order seconds to tens of seconds, and we've got lots of other information, which is probably not of enormous interest to a lot of you, but if you're interested, do check out the review that should be coming out very soon. So one of the main focuses, since we discovered that neutron stars are present in large numbers in the ULX population, is what is the strength of the magnetic field? And there are two results, essentially, or two implications. If we have a very high strength dipole field, as I show on the left-hand side, this is a beautiful picture from Alexander Mushtakov's work, you reach the magnetospheric radius outside of the spherization radius. So you never actually become locally Eddington. A material then falls through what we call an accretion curtain onto the neutron star. If we have instead a weaker or moderate strength dipole field, then the magnetospheric radius is inside the spherization radius. And it's the picture I showed you before, just this picture is way prettier. He's a very talented guy. So you can see the difference is going to be important, right? The one on the left, you no longer have strong collimation by winds. In fact, the question of winds is still an open one. The one on the right, you still get all that collimation. Luckily, the field estimates for most of these systems is coming out at less than 10 to the 13 Gauss, which implies that we're looking mostly at the picture on the right-hand side, not the picture on the left. But what that means then is that in our population of ULXs, whether they contain black holes or neutron stars, many of them are not going to be visible to us because you've got this big envelope of material, this huge wind, which is covering a large fraction of our source, and we can't see through it. A great example of this is SS433, the object I mentioned earlier, where the mass accretion rate is more than 300 times Eddington for a black hole, but in the X-rays, it's only 10 to the 35 to 10 to the 36 ergs per second. So a thousandth of Eddington. And the reason for that is just we're looking edge on. You can back extract what the intrinsic luminosity did, and I did that a couple of years ago, and it should tell us that it is a ULX if it was face on. But for those of us who want to understand the population of ULXs, we're basically missing a large component of our population. And that's going to be a problem if we want to identify some of them as neutron stars. If we're trying to look through a wind, we're not going to see the region close to the neutron star, so we're not going to detect pulsations. And in fact, even if we're face on, our pulsing region is in the middle of our wind cone, and those photons have to scatter around and then eventually reach us. And the problem there is that if your pulse period is shorter than the light travel time through your cone, you really dilute the signal. Basically, it's a sinc squared function. And so that can be a real problem. So discovering neutron star ULXs is going to be quite challenging. And I'll come back to that in a bit. One of the things that might help us with our picture is that the one I've described to you is static. But my feeling is that the community now is edging towards, and I'm doing a bit of the pushing, towards considering these winds and disks to be dynamic. And one of the evidences for this is that we see what we call super-orbital periods. So that's a period in the light curve which is longer than the orbital period. That's why it's super-orbital. And this is some work by Don Moulton and also by Jojos, where you can see an X-ray light curve with these nice changes on timescales of tens of days. And what I believe is happening is that the disk and wind is precessing around. So it's wobbling around on its axis. And one of the bits of evidence for this is that if I was to plot that top left-hand light curve, extract the counts per second against the spectral hardness, we see that when it's near its peak, it's much more spectrally hard. And so what you can imagine then is this wind cone is wobbling around. When you're more face on, you're brighter and more spectrally hard. Remember, that was one of our original models for super-Eddington accretion. And there's also indications that the wind is changing as well, and that seems to match this picture. So again, just to reinforce this picture, I want you to have in your head, when you're going from face on to more edge on, in that plot on the top right-hand side, we should expect to see X-ray emission that does this, and then lower frequencies and lower energies should look probably more sinusoidal than the purple pinky line implies. But that should be changing, and it should be changing out of phase with the X-rays. And Thomas Dowser actually created a model to describe this. So for those of you who don't know Thomas Dowser, he's the creator of the RELSIL models, which are used by basically everybody. Him and Javier Garcia created those. And he created a model to describe this called ULXLC, which is a really cool model, underused, but really, really cool. So if these things are precessing, as I speculate they are, then what we want to do to find our population of supercritical or super-Eddington sources is to look at the sky an awful lot. And one of the best tools for doing this is eROSITA, should it ever turn back on. So eROSITA is scanning the entire sky once every 6 months. Data has been acquired up to cycle 4, so a couple of years. And we should be able to use the number of new ULXs to actually tell us about how many neutron stars or black holes there are in the population. Now, describing that is super complicated, but if that's your sort of thing that interests you, please read the paper by my PhD student, Norman Kahn. It's a very computationally heavy process, but really interesting results. So eROSITA and ERAS is going to be important for finding our systems, but that's only if they're ever bright in the X-rays. Some of these systems, in fact, because you overrepresent edge-on systems in surveys, most of our systems won't ever be X-ray bright. They'll only be probably optical UV bright. So how do we find them? I've kind of given the game away with the title. What you can do is create a test population of ULXs. I work with Greg Viktorovich, who's worked with Chris Bozinski. So we have access to StarTrack, which is a binary population synthesis code. We can simulate a fake population of ULXs and then work out get the accretion rate. We've got the mass, which means we can work out the temperature of that edge-on photosphere using the formulae that I've already given you in this talk. And that tells you that up to megaparsec distances, these photospheres should be 23 to 24 magnitude. So what we would hope to do maybe is look for these precessing ULXs in Vera Rubin LSST. And in fact, it might be easier than this, because not only do you have intrinsic emission from the photosphere, you also get some Compton downscattered emission through phases of the wind. So you could have something which is many magnitudes brighter than this, and we would expect it to vary. Now, how we differentiate that from something like an LBV, not super sure immediately off the top of my head, but my hope is that we should have some simulations soon. So keep your eyes open for that. So one of the methods that I'm quite a fan of in terms of driving this precession is lens theory. Now, there are many other ways to do this, as Josh will tell you. But the reason I'm excited about it is because I think it's quite an elegant result of general relativity. So just to describe what happens, when you have material which is coming towards your compact object and it's vertically misaligned from the axis of rotation, you end up creating a torque due to frame dragging, and that causes a fluid body to precess around vertical nodes and periapsis. And there are two ways to describe this precession. It's either in the diffusive regime or it's in the wave-like regime. If it's diffusive, you just get a Bardian-Peterson configuration, which is basically static. But if you have a wave-like regime, which occurs when your scale height, your disk is large, so like in super-Eddington accretion, then you drive solid body precession. And this is pioneering work done by Christopher Gill in 2007. Our other simulations done by people like Matt Lisker tell us that, yes, this should happen. And also any jets that are created should also precess with our large scale height flow. And this was, I believe, confirmed in some really exciting work carried out by James Miller-Jones in 2019, where there was a super-Eddington outburst of an X-ray binary in our galaxy. And his team, which included me, we're able to measure, we're able to detect the ejection angle of the jets, and we could see that it was moving with time. So I think that's telling us that our inner regions are indeed moving around, and it's a black hole, which is great because actually lens-thinning precession should definitely be occurring from black holes. Neutron stars a little bit harder. So what can we do if this is actually lens-thinning precession, which is driving these supraorbital periods? So the time scale depends upon a few things. It depends upon the outer radius of our wind photosphere. That's basically the point where radiation pressure stops. It depends upon the inner radius of our disk. So either that's the magnetospheric radius or the ISCO, that's where the torque is being communicated. And it depends upon the mass and the spin of our compact object. And the other thing that depends upon, that connects all of these things together is the accretion rate. And you'll remember that the accretion rate, you might remember that T soft was related to the mass and the mass accretion rate. So that tells us where our soft emission should be if we can extract it from our spectrum. So what you can do then is create this picture where I've got my supraorbital period, I have neutron stars in there, I have black holes in there, different masses, different limiting values for the spin. Black holes can spin much faster than neutron stars. And these are all coupled together in some complicated way. In 2019, I realized that this actually should map out a region of parameter space where we can take our supraorbital period and our soft temperature, and only one bit of it should contain black holes. Neutron stars shouldn't be allowed to be in it. And the reason that I like this is that the temperature of the soft component is kind of easy to get with most X-ray instruments. So that's good. There's normally a lot of effective area. And it's easy to get these supraorbital periods as long as we're granted time on instruments like Swift. So we can combine these things fairly easily. There are issues. I'll hold my hand up. You know, this is based on analytic theory. The simulations haven't been done yet, but we are doing them at the minute. There are other torques present in the system. Tidal torques, magnetic torques, free precession, magnetic precession, and you have to account for those or consider those. With black holes, it's much easier, actually, because you don't really have any magnetic field stuff to worry about. And also, if you have a neutron star with a really strong magnetic field, then that soft temperature is no longer to do with the super-Eddington flow, it's to do with something else. Now, just to sort of whet your appetite, you can put known ULXs onto here, and the neutron stars do sit in one bit and the black holes do sit in the other, but I'm not going to bet my house on it, this being correct yet, but I think it's really interesting and it's a cool area to explore. So just in the last bit, I just want to mention other ways that we can go about trying to separate out the population. Occasionally, the neutron star accretion can switch off. And this happens when you're no longer able to basically extract angular momentum out of the material that's infalling. We have a radius called the co-rotation radius. So that's where your angular velocity is the same within your disk and in your neutron star. When that gets close to the magnetospheric radius or moves within it, then accretion switches off and we create a centrifugal barrier, which can carry material away from that magnetospheric radius. This results, unsurprisingly, in a drop in luminosity because you've killed accretion onto the inner regions. And perhaps if we see this propeller state in ULXs, that's great. It tells us immediately that we're seeing a neutron star. And there are some interesting examples which may well be due to that. Georgios has written a recent paper on this. My recent predictions in a paper that came out very recently implies that for a lot of our systems, maybe that change in luminosity is going to be very hard to spot. So maybe, I guess we'll see. Another way is to detect cyclotron resonance scattering features. So electrons are quantized into Landau levels, as are protons. And then you can scatter those electrons and protons into higher Landau levels, and that results in an absorption feature. It's not absorption, it's a scattering feature. And if you see one of those, it's telling you there's a strong magnetic field, so it can't be a black hole, therefore it's going to be a neutron star. This is an example of one in a ULX from a couple of years ago, and you can merge the various equations and you can try and estimate the magnetic field strength. Another way might be to search for jets. So this is probably the best example of a ULX with jets. This is Homburg 2X1. It's one I said earlier may contain a black hole. You can see there's lobe core lobe behavior, so it's like an FR2. And this is a fascinating source. The jet power is around 2 × 10⁻39 ergs per second, so really powerful kinetic luminosity. You can compare that luminosity to that theorized from a magnetic neutron star, and it doesn't seem to fit. So either this does contain a black hole where it's actually easy to extract energy and make powerful jets, or maybe the model is wrong. But I think it's probably a black hole. Of course, you can just get a better telescope. I think everybody hopes that Athena rises from its current issues. Athena will be amazing and groundbreaking for many fields, including ULXs. It allows us to perform very deep pulse searches and detect very many more of these systems. And also, this is an opportunity for me to advertise HEXP. So this is a mission which is competing in the small class mission for NASA. It has a very wide energy range, all the way from 0.2 to 150 keV. It has better angular resolution than NuSTAR. And I'm one of the co-chairs of the ULX working group, and we're still looking for people to get involved. If you're excited about doing X-ray spectroscopy, timing, high energy imaging, please get involved. Georgios is also involved, so ask him if you want more information. So I think just to wrap up, hopefully I'm not over time. We know ULXs contain super-Eddington accretors. This is really important for understanding this area of exciting physics. We're not breaking any laws of physics, which is always nice. The winds are going to change our view of the population for many reasons. They are precessing almost certainly, I believe, and that's going to help us to some degree. We can use modern instruments like eROSITA and Vera Rubin LSST to try and better understand the demographic. And in future, we're going to make massive strides in understanding ULXs from various different angles using all these fantastic new satellites. Thank you very much for listening, and I hope to have some really interesting questions. Thank you so much.
Thank you very much, Matt, for this excellent review on the topic of ULXs. This is quite exciting. I would say I'm very excited. It's very exciting, but I'm working on high energy astrophysics, so
yes,
it's like a biased view. Okay. So I think now it's time for questions from the audience. I see one hand raised by Apostolos Stichiadis. Please go ahead.
Yeah, hi. Thank you very much, Matt, for your excellent talk.
Thank you.
And it was very, very interesting. I have one or two questions, I'm not sure. These ULXs are time variable. I mean, what is the time scale variability?
Right, so they're time variable on everything from 1,000 seconds, which is basically where we start being nobbled by the Poisson noise, all the way down to tens of days and weeks. So that superorbital period that I showed you, those tend to be of order tens of days to maybe 100 days.
Okay, so, and you said that you find a variation of the spectrum, the hard X-ray spectrum, with time, with luminosity. When brighter, it is harder.
Yeah, yeah.
Right. And what makes you think that this might be a thermal emission, I mean, in the hard X-ray regime? And if it is thermal, is there a way of discriminating between black holes and neutron stars that way from the spectral? Maybe you said something like that, but I had my connection went down for 5 minutes, so I'm not sure.
No, I didn't say
that.
It
was,
it's an excellent question. I mean, so you look at these. Hopefully, you can all still see what I'm showing. I mean, you look at these spectra, and there's a thermal cutoff. And they look very thermal. You're not seeing something which looks obviously sort of non-thermal and power law out to high energies. That doesn't, by the way, preclude there being a non-thermal component. For instance, in SS433, there is high energy emission, which at some point must actually couple to the very, very high energy emission. We just don't have the sensitivity to it. And can you distinguish them from neutron stars from black holes? Annoyingly, probably not. So there's been some work, and I don't unfortunately think I have a slide of this. I don't, but I will show this. So there's been some work carried out by numbers of groups, Fabio Pintore, Don Walton, and if you put all the X-ray spectra of ULXs and you notice the ones that are neutron stars and the ones that aren't, you can't obviously tell there's a difference. One of the big problems, though, is that we don't really know a black hole ULX. So it becomes quite difficult saying this is one and this is the other. And the reason that people say, oh, maybe they all contain neutron stars because of the spectrum, we have to be very careful. Yes, you get extra emission from the accretion column, but when you start post-processing the GRMHD simulations, you already get more hard emission than you'd expect just from a Veen tail. So this is work I'm just showing you here, which hasn't been published yet, but hopefully will be relatively soon, where we've post-processed super-Eddington simulations carried out by Yanfei Zhang with myself. And you can describe the spectrum of this ULX without requiring an extra third component due to the accretion column. So it's quite an underwhelming, depressing answer that unfortunately I don't think you can unless you get a cyclotron feature or pulsations. But maybe I'm wrong. Maybe in the next 5 years, we'll find black hole ULXs, and then we'll be able to put them together and say, this is what they look like. These must be the neutron stars.
Yeah. Okay. Thank you, and good luck with your searches for it.
Thank you. I know what that means.
Okay. I see one hand raised by George. So, George, ask your question.
It's very interesting.
Oh, sorry, George, we cannot hear you very well. The sound is like breaking up. Can you repeat? Not very well.
Sounds like you're underwater.
Let me see.
Oh, I think that's improved.
Now?
Yes.
No, okay.
Okay. Have to always play with amplification. So thanks very much for the interesting talk and very nice results, and for referencing my work too. So I have a question which is similar to Apostolos. So when I started, my studies, my PhD studies, there was a poster outside my office that said intermediate mass black holes, ULX connections and everything. Then when I finished, it was like super-Eddington ULX sources accreting magnetized neutron stars. So quite a change within a few years. And now we have all these LIGO observations for merging black holes, and you see that you have like all these very massive black holes. And when I talk with people that do, massive stars, LIGO sources, like I was talking recently with Lida Oskinova about that, can we actually find any source, any ULX source that we are pretty confident it's a black hole? And as a next question, can we actually measure their mass without having to do like without going to an eclipsing system where we do radial velocities and being very accurate? Can we do from spectral or any other signatures sort of say that this is a ULX with 100 or 10 solar masses?
You're quite right that those LIGO results are obviously fascinating. They still don't know how those systems necessarily form, of course. There's still the debate, are they formed in globular clusters, or are they formed, as binaries in the field? 25 is high. You look at the X-ray binary population in the galaxy, that would be extreme. Not impossible, but quite extreme. So I'm not, although absolutely any system which contains a very high mass companion star almost certainly will go through something like a ULX phase. If it's in the wrong point, if it's more convective envelope, so like a red giant, then it'll go through common envelope, through dynamical mass transfer, shrinking the orbit. Maybe that's how we end up with some of these systems, but certainly ULX phases will be fairly common. Can we get the mass through any other way? Not that anybody would believe. I think that the only way that anybody will believe that we've got a black hole ULX is if we measure it dynamically. I can't see anybody else believing it. We can go through all the things and exclude it, right? And you know, I know exactly how to do that. And we say, oh, well, you can't make jets from neutron stars like that. We can't make precession like that. You can't do blah, 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 blah. And then people go, oh, you still haven't proven it. You know, I know the referees who would say that. So I think the only way to do it reasonably would be dynamically. Actually, the best example is probably SS433, where there is a dynamical mass estimate due to the bracket gamma lines, which are stationary and coming from a circumbinary disk. And there, they do believe there's a black hole, and that's accreting at 300 Eddington. Unfortunately, we're not looking face on, which is really annoying. But because we're edge on, we get eclipses, we have dynamical constraints, we can do lots of really exciting stuff. So yeah, I think we're going to have to do it dynamically, and I think that will be possible. I think if we're going to look at you know, really amazing next generation instruments with next generation spectrometers, maybe we can do this. You know, things on the ELT perhaps. Maybe even some space-based stuff can already do this because of the accuracy. Yeah, I wish I knew. If I'd known, I would have written the paper already. Hello.
Thanks for answering that. It was interesting. There was a source like near recently, like M33X7, that they measured dynamically a 40 mass black hole, but with X-ray luminosity of, I don't know, 10 to the 37 or.
Well, the other thing,
generally, is very difficult.
You know, it also becomes a little bit depressing, right? That when you try and look for masses like that, they're degenerate with hierarchical systems. There's the great example of this with the 70 solar mass black hole from a couple of years ago, that now they believe, in actual fact, it wasn't to do with a triple system in the end, it didn't do with the lines themselves and how they're being interpreted. So it's still a bit of a minefield, even when you think you've understood the system. Yeah, I don't know, but I would argue that logic dictates that there will be black hole systems out there. I mean, look at GRS 1915, V404 Cygni, SS423. Our galaxy is not that special. It's not even that big, you know, compared to other galaxies. So you can be damn well sure there'll be other systems out there that look like this. And then there's the other example of HLX1, which I think remains the most compelling argument for an intermediate mass black hole, other than in the center of dwarf galaxies.
I would like also to ask one or two questions. So we'll give some time to the participants to think of their own questions. So one question is related, Matt, to the simulations that you showed us with the radiation and the MRI in the disk. Yep. So I was just wondering if you remember, how does the magnetic energy density in the inner flow compares to the radiation energy density?
Oh, that's a great question.
So in other words, in these simulations, are the winds only radiation driven, or is also the magnetic field plays a dynamic effect in launching these winds?
It's radiation pressure dominated.
Okay.
I'm almost certain of, if only because we've just run a new suite of simulations using a different code that is radiation pressure dominated compared to, so we've done the ratio, we've taken the ratio of magnetic pressure to magnetic pressure, and it's radiation pressure dominated. Magnetic pressure is still there.
Mm-hmm. But it's not dynamically important.
No, magnetic fields in this case become important when they are carrying radiation to the surface of the flow, because it's another way of cooling it rather than through radial advection. Mm-hmm. Although interestingly, so I don't know how familiar you are with the work of Jane Dye.
No.
She's done a lot of, you've not come across her. So she's done a lot of MHD simulations, radiative MHD simulations of TDEs, and is now moving to ULXs. Mm-hmm. And one of the great advantages of her code is that you can put GR into it. And she generates jets. Mm-hmm. I can't remember whether they're pointing flux dominated or not, but she generates jets due to magnetic fields. So in that case, magnetic fields are dynamically important.
I see. Okay.
So somewhere these things need to sort of come together, I think.
Okay, I was just curious about that. It was a detail anyway, but I also noticed, I mean, going to this figure now, that there are, as you said, different parts of the outflow that have different velocities. And you showed us later on one spectrum, or your basically calculations with the absorption features, where you estimated the outflow velocity being close to 0.2c.
Yeah.
And at the same time, if I'm not mistaken, I think that the photon spectra were dominated by the soft component, so in these units. So is this always the case? Because I might have imagined that you might detect stronger absorption lines when the photon spectrum, or not stronger absorption lines that correspond to fast-moving material when you are looking within this fast cone, which means that the source will be more X-ray bright and the soft component would be less bright.
Right. So we're always going to be dominated by the features which have the greatest optical depth. So that tends to be the slightly slower moving material. They have to still be X-ray bright to be ULXs, so we can't go to extraordinary optical depths where we're not really able to see to the inner regions. But the other thing about detecting these features is that, can you see the slide I've got in a minute?
Yes.
That blue component, right? That's a real component. And I've been able to isolate that using variability tools. When you have a hard ULX, that's really bright because of I think because of geometrical collimation. And that can just totally swamp your absorption features. You just basically got continuums filling it in. So you have a combination of effects. You're looking through sight lines which have lower optical depth, and you've also filled in those absorption features with continuum emission because of geometrical beaming. So the best time to look for it is kind of in this state where it's still X-ray bright and you're likely to be decent optical depths of wind material.
I see. Okay. Yes, thank you for the explanation.
Cool.
Any more questions for Matt? Let me check the chat. I don't see any more hands raised. So I think that it's time to close our session because we have taken a lot of time, I think, from you, Matt.
That's okay. Thank you so much for inviting me and for listening to me talk on about ULXs. It's been great hearing from you. And if anybody does have any other questions, I'm happy to respond via email. Thank you again.
Thanks for being here.
Thank you. Thanks for being here. Yes, for joining. Bye.
Bye, guys.